Hey, good morning, everybody. A couple of things just want to point out that today we're on the 26th. The 28th is drop day, so if you're thinking about dropping, please come see me. I think that I've talked to everybody, but if you're thinking about dropping, please just come see me and we'll talk about it, sort of see if that's really the best decision. And then we have an exam on Wednesday, and so we have Friday and then Monday. Monday I'm planning to devote largely to review for that exam. Remember, it's going to cover chapters 5, 6, and 7, and it's also looking like it'll cover the very beginning of chapter 8. Now, before you yell, it'll be good for you because I'll tell you exactly what to expect. It's torque. We've already seen it in the lab. We've already seen some of it actually as we've been going through. So I'll show you exactly the type of question you'll expect. It'll be hopefully a give me question. So it'll help you to dilute the rest of the exam. Okay? Is there a question? No. Okay. Y'all good to go? Okay. And then we just, we're coasting until the end of the semester. We have 3 more chapters on fluids and then also on chemistry stuff, thermal calorimetry, ideal gas law, stuff that you've probably seen in high school chemistry. Okay, people? Yeah. Oh, the food drive hasn't started yet, but as soon as it starts, I think tomorrow it starts. So that'll be coming soon, and then we're going to have a couple of assessments that you'll have to take, and we'll figure out when we're going to do those, but they'll happen towards the end of the semester. Okay? 10 points for the food drive if we reach some maximum level, and then 10 points for those assessments. That doesn't mean you definitely get those 10 points for the assessments. You get the percentage that you get on those assessments. The food drive, everybody gets that, whether you participate or not, because I'm not requiring it, but I am going to encourage everybody to bring in 3 to 5 items. And then if everybody does that, then we'll reach our maximum goal. So, go through your cabinet, look for unexpired food that you don't think that you're going to use, or go to, Rouse's or Walmart or wherever you shop, and just pick up a few things, corn, beans, I don't know, not water. We're not going to do water this year. Okay? Any other questions? Y'all had a good break? Are there any big events that come in? Anybody? I'm trying to converse, I'm trying to engage with you. Were there any big events from the weekend? Yeah. Akira? Hey. You did what? Drug your foot off. All right. Let's go to the back and look at just one more kinematics question to sort of fire up the pistons here. Let's look at number 24. I don't know what exam this is, but it's the Ferris wheel problem. I think it's exam 3. Number 24. Ferris wheel rotated initially at an angular speed of 0.5 radians per second. Accelerates over a 7-second period at a rate of 0.04 radians per second squared. What displacement does it undergo in this time? Okay, we're sort of split up on what the right answer is. Please ask your neighbor what they think. We'll do about 15 or 20 more seconds. I'm going to stop at 2:05. 2:05. Okay. Let's see what we got here. All right, I think B is right. So in these problems, you know what? If you've never seen them before, they're difficult, but they're not meant to be complicated. All right, they're really meant to be reading the problems, figuring out what is what, and then plugging into the appropriate equation. So remember, we have two equations. Omega equals omega naught plus alpha t, and then we have theta equals omega naught t plus 1/2 alpha t squared. And now I want to write down what I know and what I don't know. I know that the initial angular speed is 0.5 radians per second. So that is omega naught, is 0.5 radians per second. I also know it accelerates over a 7-second period, so that's t equals 7 seconds. And the rate of acceleration, which is alpha, is 0.04 radians per second squared. And I want to know what angular displacement does it undergo. I want to know what is theta. So if I'm going to find theta, I have to use this. So I say theta equals omega naught, which is 0.5, times 7, plus 1/2, times 0.04, which is alpha, times 7 seconds squared. And what was it? D is the right answer? Was it D? So that's 4.48. The unit is radians. Okay? The kinematics problems that you'll see, they'll be similar to this. They're going to be largely one-step problems. They will be one-step problems. You need to know what is omega, what is alpha, what is theta, and be able to use those equations, those two equations, properly. Remember, those equations are on the equation sheet. We're going to use them again in Chapter 8. So we'll get into some slightly more complicated stuff in Chapter 8 where we'll begin to use these equations again. Okay, but right now, just want to sort of remind you of these kinematics equations that we saw back in Chapter 2. Okay? You with me on that? Seems like most of you have this. If not, let me know. Yeah. Oh, I did. I said the angular displacement is this theta equals omega naught t plus 1/2 alpha t squared. Is that what you mean? Oh, so that's our definition of displacement, is our initial and our final positions. But when we're talking about instantaneous quantities, like we are here, we use these two equations. You're probably not going to see average or those sorts of things, the average velocity or average acceleration, which is where that comes from. Right? We're going to see basic kinematics problems like this, using these two equations for instantaneous values. Is that clear, everybody? I want to make sure that we're clear on this. Okay. Also want to make a point, because last time I said that you can never go wrong converting to radians. And that is true, that if you have values that are in different units, that you can never go wrong converting into radians. Let me find a problem, for example. Well, I don't see one right off. But if you look at some of the old tests, well, let me show you one. Just bear with me. I have to look back at another test. So I think exam 3 here. Okay, so for example, look at number 2 here. I have a potter's wheel that moves from rest to an angular speed of 8 revolutions per second in 2 seconds. By the way, this is Fall 14, Exam 4. And I want to know its angular acceleration in revolutions per second squared. Here, I don't have to convert to radians, because I have everything in revolutions up here, and then all the answers are in revolutions. So you'll find some instances where you don't have to convert to radians. So for example here, I would say, well, I'm looking for alpha. Oh, shoot. I'm looking for... Oh. Oh. Give me a second. What problem number was that? Do y'all recall? Number 2? Okay. So I think this will work now. I'm looking for alpha, right here, the angular acceleration. Looking for alpha. I know omega here, that's omega final. I know omega naught, and I know t. And so if I want to know alpha, I would say omega equals omega naught plus alpha t, and then solve that for alpha, which would be omega minus omega naught over t. Questions like we've had in chapter 2. But notice if I keep this in revolutions per second, and then I keep my t in seconds, which is our SI unit, then my alpha is going to come out in revolutions per second squared. Now I'll say that just to tell you that it is true that if you convert all of your units to radians, then you'll never go wrong, but it's not always necessary. And in these kinematics problems, it's not necessary. Just be careful with your units, that you look at your units and make sure that the units that you're using match up with the units that you're expecting to be given. That is, the units that are in the answers, because sometimes that might change. Now in chapter 8, we'll see where some cases you'll need to convert to radians when you're working certain problems. But we don't need to worry about that right now because we're not going to see that for the next exam. Okay? Y'all follow what I'm saying? You'll never go wrong converting to radians, but you don't really have to right now anyway. Later you will have to, and we'll deal with that when we come to it. Okay, so let's look at centripetal forces. And by the way, I sent a message out, but I posted a reading assignment and a quiz. A reading assignment and an assignment, a homework assignment for you guys. It's due on Monday, the 31st at midnight. It covers, what does it cover? It covers kinematics. It covers this stuff. I think that you'll find it to be very similar to what we've been doing. So y'all go and take a look at it. Many of you can probably do right now. Remember, your quizzes count as an exam. So you want to do as well as you can on those assignments. Those 6, 7 question quizzes that you get on OpenStax, those will count as an exam. And the class as a whole is doing really well, but I'd love to see some of you do a lot better on those, because it should be 100% for y'all. All right, I want you to do everything you can to get 100%. Find somebody to work with, whatever you need to do. Do as well as you can on those quizzes. Okay? You might have another short one. I might give you a little bitty extra one, also due on Tuesday. One to cover torques that we'll do, and then also just to help you pad that grade a little bit. Okay, let's go back to centripetal forces. Or centripetal acceleration. So if I have something that's moving in a circular path, like this, I have some forces at work. What are the forces that I have at play as this thing moves around in a circular pattern like this? Okay, I have the tension in the string. So the string, or this wire in this case, is actually pulling on the object. This is just a little notebook. It's actually pulling on the object and causing it to move in a circular path. What are the other forces? Or there's another force that we have. The gravitational force. So we also have a gravitational force that is pulling on this object. But I have the tension in the string, particularly the tension here, and then also I have the velocity, and the velocity is a vector. With magnitude and direction. either one of those is change as this object is moving around in a circular path, that means that I have a changing velocity. So if the magnitude or direction change, then the velocity vector is also changing. And what do we know about a changing velocity vector? What do we use to describe how velocity changes? What is that quantity? It's acceleration, right. Anytime I have a changing velocity, then I have acceleration. So I can have something moving at a constant speed. That means the value of the number of meters per second that it's traveling, that can be constant. But if it's traveling in a circular pattern, then that means that the direction is constantly changing. So the velocity at one point is in this direction. The velocity over here is in this direction. The velocity over here is in this direction. So in the case of circular motion, with circular motion at a constant speed, the velocity is always changing. So we have acceleration. If I have a changing velocity, I have to have an acceleration. Now, this isn't the type of acceleration that we've seen before. It's a little bit different. We call it a centripetal acceleration. This centripetal acceleration centripetal, by the way, means center seeking. And that's in contrast to another type of acceleration that we call centrifugal acceleration. That's an imaginary thing. Have y'all heard that song by It's Centrifugal Motion? Y'all know the song I'm talking about? Faith Hill, I think. Do y'all know where she's from? Megan, do you know where she's from? What's her name? Faith Hill. Where's she from? She's from Mississippi. Oh yeah, but she's from Mississippi. You know. Who cares about Tim McGraw? There are many famous people from Mississippi. And this is where my wife would roll her eyes. Because there are no famous people from Missouri, which is where she's from. It's like Harry Truman, is it? Harry Truman, who's that, right? But there's William Faulkner, B.B. King, right? He's from West Point, I think, right? Who else is from Mississippi? That's famous. That's two already. Elvis Presley, not from Tennessee, Mississippi. Tupelo. Did y'all know him from Mississippi? Yes. Okay, but anyway, centripetal acceleration means center seeking. That centripetal acceleration we'll call A with a subscript C, and it has a value equal to v squared over r. Where v is the speed, and r is the radius of motion. All right, we can substitute. We know that this is true. Remember, we had those equations where we could translate our angular quantities to linear quantities. We said that S was equal to theta r, V was equal to omega times r, and A was equal to alpha times r. Now be careful, this is not centripetal. This is our tangential acceleration. It's different from our centripetal acceleration, and that's why it doesn't have a subscript. It means that if I have something that is accelerating at an angular rate, that the corresponding linear rate of acceleration is equal to a. So if this thing is going slow first, and then it goes faster and faster and faster and faster, then it's accelerating at a rate of alpha in radians per second squared, but the linear distance over which this thing covers is accelerating at a rate of a. This is not centripetal acceleration. It's measuring, if you were to take the path, the circular path, and stretch it out over a straight line, then this would describe the acceleration of that object as it travels along that straight line. Y'all with me on that? Okay, those are different things, the tangential acceleration and the centripetal acceleration. But, so back to what we were saying, that if we substitute this v equals omega r, then we get ac is v squared over r. That's going to be omega times r squared over r, which is omega squared r. So we have two alternate expressions for centripetal acceleration. Both of them are on your equation sheet. And, you know, you can use either. If you know omega, if it's given in a problem, then just use omega. But if you know omega and r, then you can also find v, because v is equal to omega times r. Two expressions for centripetal acceleration, so omega squared r and v squared over r, and they're both the same. Now, if we have an object that is accelerating, yeah, go down from here, yo. Oh, what is that? Sorry. If I have an object that's accelerating, then I must have a force. And that force we call the centripetal force. Now, this always confused me. I never really understood the centripetal force until I realized that the centripetal force is really just a name that we give to a force that already exists. So for example, in this case, when I have this object that's traveling around in a circular path like this, what is the centripetal force that's causing this object to travel the circular path? What force forces this thing into a circular path? The tension in the string. So in this case, the tension, it is the centripetal force. You can think of other things when objects travel in circular paths, and they have different centripetal forces. Like, for example, you ever ride that thing at the fair that spins you around real fast? I think they have it at the volunteer, at the fireman's fair. You know what I'm talking about? And you suck up against the wall, and then it lifts you up? Yeah, seriously. Listen, what is the centripetal force in that case? There's no strain tied to you, right? What is it? No, it's not the gravitational force, because remember, the acceleration is center-seeking. The force always has to be towards the center of the circle. The gravitational force is straight down. That's not towards the center of the circle. It's not going to cause you to move in a circular path. What is the centripetal force in that case? The wall, right, the normal force. So on those things, it's the normal force. The wall is pushing you against your back, which is causing you to move in this circular pattern. What is another, what about on like a motorcycle or in a car when you go around the curve? What is the centripetal force there? What causes you to move in a circular path? The frictional force. So in that case, the frictional force is the centripetal force. And if you don't have that friction, then what's going to happen to you? You'll go straight instead of going in a curve, and that's how we have accidents. All right. So for example, here, if I take away the tension, then it's going to not travel in a circular path. It's going to travel in a straight line path. It'll travel out straight. It doesn't continue moving in a circular path, but just slowing down. It no longer travels in a circular path, just like the car that runs off the road. If you don't have enough friction, then you're going to run off the road. All right, guys? You with me? Okay. Daniel, you with me? Okay, good. All right. So let's see here. The centripetal force in the example of the hand and the ball like this, when I'm throwing something around, the centripetal force is caused by the tension. It is this force that causes the ball to change the direction. So the tension is the centripetal force. So we have some other things like we talked about, like this thing that spins around like a salad spinner. In this case, the normal force is our centripetal force. Notice that it's directed towards the center of the circle. It's the centripetal force. Or we have a car going around a corner. In this case, what is the centripetal force? The frictional force between the tires and the road. By the way, is it static friction or is it kinetic friction between your tires and the road? I don't answer right away. Think. Is it static friction? Is the surface of your tire moving relative to the surface of the road? Or is it, we could call it kinetic friction also, is it doing like this? Which is it that between the surface of your tire and the road? Is it static or kinetic friction? It's static friction. So in this case, I have static friction. In fact, as we saw in chapter 4, static friction is almost always bigger than kinetic friction. So that's good. You want your tires to keep moving. That's why we have things like anti-lock braking systems, because it keeps your wheels moving so that the static friction will stay in play, that you don't get kinetic friction, which is a lot less. That's when your tires start skidding across the asphalt. Okay, so we can calculate the centripetal force, and we'll have to later. F is equal to ma. I'm going to call this Fc for centripetal, and that's equal to m times v squared over r. Let me put a little thought bubble over here. You don't need to write this down unless you think you might see this again. Sometimes we see the centripetal force not written as Fc, but written as Fr. And this R means radial, because the centripetal force is always acting radially. So if you see this on the MCAT or wherever else you might see centripetal forces, you might see it listed not as a Fc, but as an Fr, because it's a radial force. It acts along the radius of your circular path. Okay, let's try a quick test. All right, so you have this object that's traveling along in a circular path. What would happen to the object if you cut the string? If you could cut the string at this instant, right here, and take away the tension in the string, what would happen to the object? What path would it take? All right, we'll stop at 1 minute. 1 minute. Okay, good. B is the right answer. A number of you put D. It actually went down. But a number of you put D. And I understand that if I take away this tension, if I take away this force, then you imagine that this object is going to move in the opposite direction, because this force is no longer pulling it in this direction. But don't think of the force of the tension pulling it opposite D. Really, you want to think of the force of the tension as pulling it into a circular path. And so if I take away that tension, if I take this away, then the object is going to continue on in its current velocity vector. And its current velocity vector is in that direction. If I take away this force, which is the centripetal force in this case, I'm going to no longer have acceleration, and so I'm going to continue at whatever my velocity is, and my velocity at this point is in this direction, take this away, it continues in that direction. By the way, let's think about something. We can write it here, it's fine. If my centripetal force, which in this case is the tension, is equal to m times v squared over r, what happens, the tension has a maximum value, right? Like if I have a rope that's applying tension, eventually my tension is going to cause that rope to break. So what happens if I increase the mass, or v, or if I increase or decrease r? What's going to happen to that centripetal force? If I increase the mass, what happens to the centripetal force? It increases as well. So if I increase the mass, that means that the tension needs to be greater in order to cause that object to move in a circular path. So, for example, if I also increase the speed, that's the linear speed at which this travels, then eventually I'm going to go so fast that the tension, it'll just break. You follow me? Yes? So let's see, this should work. I've never done this, so it might not work. But this is just an alligator clip attached to a notebook. Y'all watch out, because I don't know where it's going to go. But eventually, if I go fast enough, it'll come loose because it's not strong enough to hold it. Y'all ready? You never know where it's going to hit. Okay, so as you increase the speed, then the force required to pull it into that circular path increases. That's why you go slower in curves, right? Because if you go too fast in a curve, then you need too much centripetal force that's not provided by the frictional force. Let's look at this next problem because it's similar to that idea where you have a truck that can go around a flat curve with a certain speed. And now I want to know what happens to that speed, that maximum speed, if it has a radius of 75 meters. Now I want to remind you that the static frictional force is mu times the normal force, and that's equal to, if it's a flat curve, which this is equal to mu times mg. So the static frictional force is equal to the coefficient times the mass of the object, which is the truck in this case, times g, which is the acceleration due to gravity. We have two situations. One is a curve like this with a radius of 120. And the next is a curve that's tighter with a radius of 75 meters. My maximum speed here is 25 meters per second. I want to know now what is the maximum speed on this tighter curve. Think first, is it more or less the speed? And then that can, limit some of your answers. And then try to figure out what that actual speed is. Okay, y'all are doing good. Most of you, a few of you have answers that are not reasonable, but most of you have correctly chosen that the answer either has to be what or what? A or C, right? Because if I go around this tighter curve, then I have to go more slowly, right? So if it's 25 here, I either have to have A or C. So B and D just don't make any sense. We can't have B or D because I know that my speed is not going to increase as the curve gets more with a shorter radius. My curve gets tighter and a tighter curve. All right, let's do about 10, 15 more seconds. I'll stop at 2:05. $2:05. Okay, so we have A and C. What you want to do here, there are a couple ways that you could do this, is you don't know what mu is, right? And so you need to figure out what mu is. And so you could say, well, my static frictional force, that is my centripetal force. So I have mu mg equals mv squared over r. And look, you don't know the mass either, which is good because you don't need to know it. It cancels out. And then we can solve for mu. So mu is equal to v squared over gr. And that's equal to 25 squared over 10 times the radius, which is 120 meters. I'm using the data that I have for this curve in order to calculate what mu is. So 25 squared, I get 0.52. All right, and then you go to this curve and you say, well, for this one, Fs is equal to Fc, that is mu times m times g is equal to mv squared over r. M's cancel, and I'm solving v, which is the square root of mu gr. I just solved that for g, and now I can find out what is my new v. It's going to be the square root of 0.52 times 10 times the radius, which is 75, which is I get 20. So A is the right answer. Alan? Did you do a ratio? Yeah. All right. Oh, she asked. Yeah, so she asked, how do we know to not use the acceleration A equals v squared over r? Well, I did use the A equals v squared over r, where I have this v squared over r here. My mass is canceled out. Let me take another look here to see. Hold on, before. So how did you... What did the I don't think that works. I'm not sure that's going to work. I'm not sure. Okay, Maggie, how would you know? Well, looking at the problem, you would say, I have something that's moving around in a circular path, and I know it has to be asking about centripetal forces because I have a force that's pulling this object into a circular path. Usually when you have problems, we're going to be dealing with things that are dealing with not acceleration, but forces. Does that clarify it at all? I'm not sure if I answered your question.
Yeah, I just don't, like, so what do we use these formulas for?
Well, that is what we use. So we said that she asked what we're using our mv squared over r. We say that our static friction here is equal to mv squared over r. That does come into play, but you also have to know how to find the friction. Okay?
Yeah.
Okay, good. All right, let's try this one. This is more of a kinematics problem. Particle moves in a circular path of radius 0.1 meters. There's its speed. What is the acceleration of the particle? I'm sorry. Yeah, what is the acceleration of the particle? So I have this object moving at a constant angular speed. What is its acceleration? what type of acceleration am I talking about here? Am I talking about a tangential acceleration, or am I talking about a centripetal acceleration? I'm talking about a centripetal acceleration. I know that because it's moving at a constant angular speed. So there is no tangential acceleration because alpha here is equal to 0. Because it's moving at a constant angular speed, alpha is equal to 0. Right? Omega is constant, so alpha is 0. And since alpha is 0, A is equal to alpha times R. That's equal to 0. So instead, I must be asking about centripetal acceleration. What is the centripetal acceleration of this object? What kind of actions you'll need to make here about the acceleration and the speed. All right, let's do about 15 more seconds and we'll stop. We're all over the board. I'll show you how to do it. So I'm going to stop at 310. 310. Just guess if you're not sure. Okay, so we're sort of, I think E is the right answer, but let's see. Okay, so first of all, y'all are going to hate me. But first of all, like you might already hate me. You don't hate me, do you? No. You have to convert your revolutions per second to radians. The reason is, when I'm using these equations, S equal theta R, V equals omega R, and A equal alpha R, when I use these, the angular quantities here, they have to be in radians. If you forget that, remember the circumference of a circle, C equals 2 pi r. It comes from this, letting theta fill the full circle. So theta is in 2 pi, so that's radians for the circle. So I'm going to do it two ways. First way, I say omega is 5 revolutions per second. I can convert this into radians per second. I say 1 revolution, 2 pi radians. That's equal to 10 pi radians per second. Then I say AC, that's my centripetal acceleration, is omega squared times R, 10 pi squared times R, which was 0.1. This is my radius up here. And so that's 100 pi squared times 0.1. So that's going to be 10 pi squared. Because I have two expressions for the acceleration. I'm going to do it that other way here in just a second. Let me just remind you that that AC is equal to V squared over R, or AC is equal to omega squared times R. There are two different expressions. To get this one, I say V is equal to omega times R. All right, that's a good question, Chandra. Thanks for asking it, because I know that some others made that same mistake. How do you know? Doesn't matter.
So would you use omega when it's asking for and when it's asking for
No, it doesn't matter. Let me show you. There's another way. You have the same question. Should I use omega or should I use v? Let me show you the other way to work this. I could also say the centripetal acceleration is v squared over r, and v is equal to omega times r. Omega is 10 pi. R is 0.1. So omega then is equal to pi. Or excuse me, v is equal to pi. I can substitute that in, and I get v squared, which is pi squared, divided by r, which is 0.1 meters. And this is equal to 10 pi squared. It doesn't matter which one you use. It just matters, I use this one because that's what I had, because I had omega. You can take that extra little step and figure out what v is, and if you want to do that, that's fine. Figure out what v is, and then you can solve v squared over r. No, omega is not the same as v, so be careful of that. Yeah.
So, like, if you give this in a box like this, it's never be only omega.
If I give the angular speed, that's omega. If I just give the speed, if I just call it speed, then that's going to be a linear speed. That'll be v. And check your units, too. If you're uncertain, I'll always give the units. This is in revolutions per second, so that's an angular speed. If ever it's in meters per second, that's a linear speed. I know that it's a little confusing right now, but as you practice this, it'll become more familiar to you. Y'all believe me? Yeah. Okay. Yeah. Well, that is this. So, yeah. Sure. But it is the same as this. Omega r squared over r is this. Omega squared times r. Okay? All right. Let's do a few minutes of, I think we have some more clicker questions on this chapter. Am I right about that? Have we started them yet? We did. Did we finish? Just two left. We do this one? Okay, I'm gonna help you through this one. So, because we haven't dealt with this, but it's important. A child who is swinging as she reaches the lowest point in her swing. So, I have a child that's swinging back and forth, and there's a rope. It's attached to that child on the swing. And she swings back and forth like this. Now, at the bottom, right here, what are the forces that are acting on her? I have two forces acting on her. What are they? The gravitational force, the weight, and the normal force or the tension would be the same. I have the seat pushing up on her, but we can also think of that as the tension of the string. So I have two forces acting. I have the force that is up, that is my tension, and then I also have the weight. Now, the sum of the forces is equal to the mass times the acceleration. The sum of the forces is going to be Ft minus Fw. And my acceleration here is not just any old acceleration, it's my centripetal acceleration. So it's equal to mv squared over r. So with that, let's think about this. So the tension in the rope is equal to her weight. Is that true? Is the tension equal to her weight? That is this value equal to this value? Is A a true statement? Is the tension equal to the weight? Well, in order for the tension to equal the weight, this would have to equal what? 0. And it's not 0. We know that because she has a speed and a radius. How about this? The tension in the rope is equal to her mass times acceleration. Is that true? That's not true either. Now, if this was equal to 0, then that would be true because this is her mass and this is her acceleration. So this isn't true. How about this? Her acceleration is downward at 9.8 meters per second squared. No, that's not true either. That's just, she's not going down at all. She's going in the circular path. So what is the correct answer here then? D is the right answer. All right, so everybody put D. Everybody. Awesome. One more. Oh, you're just trying to be honorary now, right? Okay. Let's stop this. Hey, good job. A rigid object is rotating with an angular speed that's negative. Omega is less than 0. The angular velocity vector and the angular acceleration vector are anti-parallel. That means they're in opposite directions. The angular speed then is what? Is it clockwise and increasing, or one of these other options? Question. Remember, our clockwise is negative, counterclockwise is positive. What does it mean that they're anti-parallel, the acceleration vector and the angular velocity vector? What does it mean that if they're in opposite directions, does that mean it's speeding up or slowing down? All right, we'll stop at 110. 110. Just guess if you're not sure. 110. Okay, so if the omega is negative, that means it's clockwise or counterclockwise? Clockwise. So it has to be either A or B. And if it is anti-parallel, they're speeding up or slowing down. They're in opposite directions, slowing down. So B is the right answer. Y'all have a great day. Well, next time we're going to look at torques. We're just going to look at like the first couple of pages of chapter 8, but that will be on the exam.